Let's turn our attention now to the geometry of parameterizations. Let's say our parameterization is given by bold x of two input variables, maybe called s and t. And let's label the output coordinates as the functions x of st in the first coordinate, y of st in the second coordinate, and z of st in the third coordinate. Given this setup, we define three important vectors. The first important vector is bold t sub s, and this is obtained by taking the partial derivatives of all three output coordinates of the parameterization. The second vector is defined similarly. This is bold t sub little t, and this is the vector obtained by taking the three partial derivatives of the three output coordinates of our parameterization. The third important vector is just called bold n, and this is defined as the cross product of t sub s with t sub t. Now, this bold n is a very important vector, and it will be sticking with us for the rest of the course. This vector is called the standard normal vector. This scheme allows us to introduce adjectives that describe surfaces. We say that a surface S is smooth at a point P, which is obtained by plugging in maybe S naught and T naught into the parameterization, if the standard normal vector evaluated at those values of S and T is not equal to the zero vector. So we say that a surface is smooth at a point if its standard normal vector is not the zero vector at that point. So here's just a generic visualization of a surface. The idea is that if we choose a point on this surface, we can define these first two vectors, t sub s and t sub little t. And the idea here is that these two vectors are actually tangent to the surface at that point. And when we take the cross product of those two vectors, we produce the standard normal vector, big N. And the idea is that big N is orthogonal to the surface at that point. So we say that the surface is smooth at a point if its standard normal is not the zero vector. The opposite of being smooth is what's called being singular. We say our surface is singular at a point if its standard normal is the zero vector. So in this generic figure here, we're looking at a point on our surface that is smooth because the standard normal as depicted is certainly not the zero vector because it clearly has length here. Okay, so that's a generic looking example. Let's actually do a specific example where we calculate these vectors. So let's look at the parameterization where the variables here are r and theta. And here, let's say r ranges between -1 and 1, and theta ranges between 0 and 2 pi. The outputs of this parameterization are x is r times cosine theta, y is r times sine theta, and z is equal to just r. So we have our x, we have our y, and if x is r cosine theta and y is r sine theta, what this means is that our z actually obeys the equation z squared, which would be r squared here, equals x squared plus y squared. So what we're doing is we're invoking the idea of cylindrical coordinates to define, in this instance, a cone. So the underlying surface of this parameterization is a double cone because we're studying the equation z squared equals x squared plus y squared with this particular parameterization. So the surface that we're studying looks like the double cone. For this data, we now want to look at our two tangent vectors in the standard normal vector. our first tangent vector will be t sub little r, because little r is our first variable for this parameterization. The way the tangent vector is defined is we take derivatives of each of the outputs of this parameterization with respect to the variable little r. So here, if x is r cosine theta, the derivative of x with respect to r is just cosine theta. If y is r times sine theta, then the derivative of y with respect to r is just sine theta. And if z is equal to r, the derivative of z with respect to r is equal to 1. So our first tangent vector is cosine theta, sine theta, 1. Let's look at our second tangent vector. For this one, we're differentiating each of the coordinates with respect to theta. Well, if x is r times cosine theta, then the derivative of x with respect to theta should be negative r times sine theta. If y is equal to r times sine theta, then the derivative of y with respect to theta is equal to r times cosine theta. And if z is equal to r here, then the derivative of z with respect to with respect to theta should just be equal to 0. So our second tangent vector here is equal to negative r times sine theta, r times cosine theta, and 0. So now that we have our two tangent vectors, we can define the standard normal vector by taking the cross product of these two vectors. Well, how do we take the cross product of these two tangent vectors? Well, we can look at the formula. To cross t sub r with t sub theta, what we're doing is we're lining up three different determinants where we're deleting certain coordinates of these two vectors. So if we put these two vectors into the rows of a matrix, the cross product is obtained in the first coordinate by deleting the first coordinates and taking a determinant of whatever's left over. So we're going to take a determinant of the 2 by 2 matrix where the first column is sine of theta and r cosine of theta, and the second column is 1, 0. Then in the second coordinate, we're negating the determinant of what's left over when we delete the second two coordinates. So now we're looking at cosine theta, negative r sine theta, and then 1, 0. We'll take a determinant and then we negate. And for the third determinant, we're deleting the third coordinates of these two vectors and taking a determinant of the resulting 2 by 2, where here the columns are now cosine theta, negative r sine theta, and then sine theta and r times cosine theta. Well, when we take these determinants, what do we get? For the first coordinate, we should get 0 minus r times cosine theta. So we get negative r cosine theta as our first coordinate. For our second coordinate, we take 0 and then minus a negative, so that's plus r sine theta times 1, and then we negate to get negative r sine theta. And then finally, for the third coordinate, we're taking r times cosine squared theta minus a negative, so plus r times sine squared theta, which after using the trig identity cosine squared plus sine squared equals 1, gives us the third coordinate, which is simply equal to r. So now we have our standard normal vector, which is negative r times cosine theta, negative r times sine theta, and then just r. Now we can look at this standard normal vector, and we can use it to ask ourselves, where is this surface smooth? So remember that smooth means that our standard normal vector is not the 0 vector. Well, to figure out where we're smooth, what we could do is we could figure out where are we singular, which means what can we input in terms of r and theta to force this vector to be the 0 vector. Well, if we look at the third coordinate, what we see is that if we set little r equal to 0, we force this vector to be the 0 vector. And in fact, that's the only way to force this vector to be the 0 vector. So the only singular point on this double cone occurs where the radius little r is equal to 0. And of course, the only point on this double cone where little r is equal to 0 is right where the two cones meet each other, right at the origin. So that's the only singular point on this cone. which we can note here. This is actually one of my favorite examples of a surface. This is a cool surface because it's smooth everywhere, but except for the origin where we have exactly one singular